As Dave alluded to, I'm going to talk about convective organization and modeling for the North American monsoon. So just a little bit of information on the picture here. How do I activate the pointer? Oh, there it is. This is actually taken on a flight from, of all flights from Los Angeles to Yuma, Arizona. You would never think you would see convection like this on a flight, but that happened to be a very active monsoon precipitation day where there was actually severe weather in the Yuma, Arizona area. When the flight landed, a dust storm subsequently hit Yuma, and we landed about like 10 minutes right before the dust storm hit. And of course, I told the pilots that they did a fantastic job flying this plane. This is one of the most scariest flights I've been on. But I got some really good pictures of monsoon convection out of it. So this is, I'm going to start out a little bit basic with some motivation, is why do we care about severe organized convection? And these are predominant monsoon severe weather hazards in the Southwest. And the same thing basically applies if we're talking in Mexico as well. Dust storms or haboobs, flash floods, microburst with severe downburst winds, and lightning. And of course, we've alluded to in the discussion yesterday, are these going to potentially worsen with climate change? So before we go into what is necessary in a regional atmospheric model for getting monsoon thunderstorms right, just let's take a step back and think about some of the basic prerequisite meteorological conditions necessary for strong monsoon thunderstorms. Organized mesoscale convective systems is basically what it is. So first we need thermodynamic criteria, heat and moisture. So atmospheric instability, where we're cooling the atmosphere aloft, warming it below, facilitates the development of cumulus clouds. That's our metric of convective available potential energy. And then atmospheric moisture transported from various sources that Yolande, I'm sure, discussed at length in her talk based on Francina's work. And as has already been discussed, a very robust metric for that here in the monsoon region is the column integrated precipitable water. And then, so if you at least have the thermodynamics conditions going for you, you get typical air mass type thunderstorms that are on the scale, that are very small localized scale, kilometer scale, forced by the diurnal mountain valley circulation, and then that follow closely the diurnal cycle of heating of the terrain, forming over the mountains during the late morning to early afternoon, and then reaching a mature stage by about mid-afternoon. So here is a really good photo from the top of Kip Peak, just west of Tucson, where you see these typical air mass thunderstorms with their gust fronts right during their most mature stage. Now, if we want to get organized, more organized type convection, we need to consider the dynamic criteria. This has also been alluded to in other talks in this meeting, the monsoon ridge positioning, the presence of some upper level disturbance, Jamie mentioned that in his talk, and then the presence of some sort of low level transport of moisture, Gulf surge, which equals that dynamically the presence of these upper level disturbance and ridge positioning leads to large scale upward motion, which you can be considered quasi-geostrophic induced vertical motion, and then a vertical wind shear, which is more the effect of on the mesoscale to facilitate convective organization, and then an injection of low-level moisture via a dynamic mechanism. So Jamie also talked about the presence of an inverted trough. Just to give a little bit of background on these are upper level disturbances that tend to form on the southern side of the monsoon ridge. They take tracks along the southern side of the ridge going from east to west, and on either side, these are favorable areas for upward vertical motion, and they are also contribute to enhanced vertical wind shear. Both facilitate convective organization. The importance of the quasi-geostrophic dynamic forcing versus the wind shear mesoscale type forcing is not exactly clear, but certainly both exist in a situation like this. And then also we have Gulf of California moisture surges. So these are triggered typically, the deep surges are typically triggered by the passage of an easterly wave or tropical disturbance, hurricane here in the eastern tropical Pacific. It intensifies the pressure gradient through the Gulf of California, has been alluded to in previous talks. So, and then the Gulf of California then acts as a channel to surge the moisture into the southwest, where it fans out along the low deserts here in Arizona. The surges in Arizona typically are monitored right here in the northern end of the Gulf of California. Yuma is the typical observing station in Arizona, but I will show that really where we need to observe these things, a very critical observing point here in Mexico is right here in Puerto Peñasco, where we actually had a GPS site. So I'll be talking about Peñasco a lot later in the talk. So this is important because in where the moisture comes from, this is really when you're talking about trying to get organized mesoscale convective systems that propagate westward off this mountains. This low-level moisture source is really critical from the Gulf surge to prime the lower levels of the atmosphere to supply moisture for the propagating convection. So with all of the right conditions, thermodynamically and dynamically, we can get convective organization and propagation. And this was well described in a paper by Steve Nesbitt that was one of the papers that came out of the North American Monsoon experiment back in 2008. So in this process, the convective clouds form over the mountains in the morning. So this is 11 a.m. local time. And then by the afternoon and evening, the storms propagate to the west to the Gulf, towards the Gulf of California. If you're in Arizona, they propagate off the Mogollon Rim towards the Colorado River Valley, but it's basically the same thing. And then they can organize into mesoscale convective systems if there's sufficient moisture and instability. So when you're talking about the late afternoon to early evening hours, and in the case of MCS development, this has been alluded to before in presentations. You have a large organized convective structure with a leading convective line, a trailing stratiform precipitation region that spans on the order of 100 kilometers or so. And you saw in Jamie's presentation when these things develop, they're fairly large. They can cover the size of the entire, a significant part of the state of Sonora, for example. And then I would also say that there are certain dynamical structures that we look for associated with mesoscale convective systems, inflows, outflows, that were characterized and worked by Bob Howes and others. So we basically want to see, when we have a modeling system, can we get this reasonably right? And then, of course, these things, as they propagate westward towards the Gulf, then they decay in towards the late evening to early morning hours. So I'm going to say straight up that the name literature, including what I will show that my group has done, has collectively shown that we need the so-called convective resolving scale of less than 5 kilometers to represent this process reasonably correct. If we're considering even, I say global models, but also regional models at scales of tens of kilometers where convection is parameterized, can't get this reasonably right. So here is kind of the, if we're looking at satellite imagery, like as a weather forecaster might, here's what I described in terms of a picture, very similar to what Jamie presented. So on a active severe weather day in Arizona, for example, we have the presence of an inverted trough traveling around the southern side of the ridge. We have moisture surging up the Gulf of California, and the result is the thunderstorms, which originate here on the Mogollon Rim or on the Sierra Madres, can then organize and intensify and move westward towards the low deserts and the Gulf of California. And notice here you see the presence of the tropical cyclone that's triggering the surge. So here is just a satellite animation of an active monsoon day. ¿Se puede activar eso? No. No sé. Sí, es una animación. Si no, necesitamos avanzar, si no. Okay. Well, anyway, what this shows is very similar to the animations that Jamie showed. Sí, haz clic. No. Okay. Pues. All right. Let's go on. We don't have time. Jamie showed similar animations in his talk where you just basically see, with the presence of a inverted trough, the convection blows up in the afternoon here. So simulation, now to our modeling work, we've simulated name-intensive observing periods with the weather research and forecasting model. So this is work I did with a master's student, Bill Kessel. So the part one of the study was to simulate several key name-intensive observing periods. So what do I mean by an intensive observing period? This is where, during the field campaign, that so-called interesting weather was forecast, namely the development of organized convection. And so we do that in short-term numerical weather prediction type experiments, actually using the almost the same experimental design as what Jamie described in his presentation, where we have explicit representation of convection on the 2.5 kilometer interior grid. So we're shutting the convective parameterization off, with the goal of establishing the value added of convective resolving modeling for organized convection. So when I say value added, it's that you can explicitly see you get some semblance of an organized mesoscale convective system structure in the simulation. And then part two, which relates more to the GPS data, TPW assimilation that we're trying to do with Yolande, Avi, and Jamie, is to estimate the model sensitivity to the specification of initial conditions. So in a quantitative way, to determine hotspot regions of data sensitivity, we're changing the initial specification of data has the impact on the forecast. So the name intensive observing periods are all indicated here. The most well-studied of all of them is name IOP2, which took place the 12th through the 15th of July. So this particular name IOP had all of the requisite meteorological conditions for severe weather. It had a Gulf surge, it had the presence of a tropical cyclone that triggered the surge, it had the presence of an inverted trough, and there was development of organized mesoscale convective systems that affected Sonora and Arizona. So here is the, considering IOP2, at least for the 14th of July, the WRF accumulated model simulated precipitation, and then the equivalent radar accumulated precipitation, and we're working on generating the equivalent TRIM data. But the most important thing you can see here is that as we go from the approximately the time of the early to mid-afternoon where convection is starting to build on the mountains, and then you go towards the late afternoon to early evening hours on the 14th. And here you can see the development of organized convection with a clear leading line and hence associated with an MCS that developed in Sonora. And so one thing we were interested in when we simulated this case, as I mentioned, it's well studied, especially by the group of folks from Colorado State working with Dick Johnson and colleagues. So this is work from a master's student of Dick Johnson's published back in 2007, and he looked at wind profiler data collected from Puerto Peñasco. And just what you're seeing is the time series of the wind profiler data with the wind speed indicated here in the colors here, with height up to 2 kilometers. And you can see that here is the surge occurring between the 13th and the 14th, and it's through a fairly deep level up to about 1.5 kilometers, and its occurrence is fairly abrupt. And other work that these folks have done has shown that the occurrence of the abruptness of this surge and its depth is due to an outflow boundary from a mesoscale convective system. So we tried to see, can we replicate that in the model simulation so you're seeing approximately the same equivalent figures generated by the WRF simulation. So this is the 30-kilometer domain, the 10-kilometer domain, and the 2.5-kilometer domain. Now, the first thing you'll notice in all of these simulations is this is when the original surge occurred in the observational data. We have the problem, independent of whatever grid we're considering, is that there's a sensitivity to the initial condition problem, and that just using straight GFS forcing, we're not able to capture the timing of the surge quite right. But the model does get a surge on the subsequent day, and that's associated with the development of mesoscale convective systems. And you notice that in terms of the physical characteristics of the surge, in terms of the abruptness and the depth through the atmosphere, the one at this 2.5 kilometer domain seems to have the closest resemblance to the observations as I just showed in the previous slide. Now, more importantly, looking at a cross-section of the development of the mesoscale of the convection is in the 10-kilometer domain versus a 2.5-kilometer domain. And what we're looking at here is a cross-section across the area of most intense convection where the mesoscale convective system occurred in Sonora. The exact dimensions are given here, but basically this is the crest of the Sierra Madres, and over here is going towards the coast, towards the Gulf of California. And so the most important figure I want to show in this presentation is probably these two, which is comparing a 10-kilometer domain where convection is parameterized. So what you're seeing is model-generated equivalent radar reflectivity versus where convection is explicitly represented on the 2.5-kilometer grid. I would maintain that this really shows in a quite dramatic way the difference of the convective resolving scale versus not. It makes a difference between you're getting some reasonable representation of organized mesoscale convective systems versus you don't. The arrows give are the scaled wind vectors with approximately 1:10 ratio of the horizontal versus vertical winds. When you do that, you can see that you see the inflow into the storm here in the leading convective line. You also can see the outflow, the rear inflow jet, and the trailing stratiform. Dave Adams and I have had lots of debates about this figure. This is a cross-section. I think I would claim, you can debate, it doesn't get the complete reflectivity here associated with the ice phase, but you get trailing stratiform precipitation for sure. You get a leading convective line. You get the structures of the winds associated with the classical known MCS structure. And you get it in a much dramatic way just from going from 10 to 2.5 kilometers. And more importantly, from the standpoint of, can you get something that is reasonably well in your model that you can say you can forecast intense convection? The answer is yes. So these other figures are just some representation of the zonal wind that just show the inflows and the outflows, and then the updrafts and downdrafts within the storm. And so again, confirming it really means the difference between you're getting it versus you're not.
Sorry.
Yeah.
Just a technical question.
Sure.
It's from the same simulation and an ST?
Yes, correct.
But then usually you go into 1/3 or 1/5.
As long as your ratio does not exceed about 6 to 1, it's okay. So
you go into 1/3?
Yes. Yeah, you're going from 10 to 2, 10 to 2.5. Yeah, that's the nesting.
So each grid is divided by 4.
Yeah. So as long as you're not exceeding a ratio of about 1 to 6 in your nesting, and this is exactly consistent with what Jamie did too. So in fact, he based his design on these experiments. So.
Usually it's recommended to go about 1/3 or 1/5.
It depends. Yeah, it depends on. Yeah.
Chris?
Yeah.
I know we don't have a lot of time. I just wondered if you, maybe you're showing it. Nope. For these, have you looked at the outer domain to see, because 10 is always kind of the no man's zone for the convection.
The outer domain,
Similar.
yeah, similar.
Okay.
Yeah, similar. I mean,
And one last
Yeah.
question. What microphysics parameterization did you use?
it's the same one as Jamie used. Yeah. Yeah.
Yeah.
Okay.
Yeah.
One of the standard.
Yeah, one of the standard ones. And I'm not trying to focus on that too much because I want to argue,
We
yeah,
don't have
yeah.
the bright band.
We don't have the what?
The bright band
Yeah,
could be
yeah,
related to
yeah.
the microphysical
Sure.
parameterization.
Correct.
And then this just is at a later time going towards the night, and this just shows the decay of the MCS and its propagation. So then we also did adjoint modeling, which gets at this issue of determining the forecast sensitivity. So this is the process where we run WRF forward as a nonlinear atmospheric model. We determine what's called a response function in a specified geographic area. So this could be something that is related to convection. We chose, for example, moisture flux convergence. We also chose some other variables, which I'll discuss in a minute. But then to determine the forecast sensitivity, we're taking this response function and then running a linearized model or adjoint model backwards in time to determine the sensitivity with respect to the initial conditions. So I don't, unfortunately, have time to get into all of the details of the mathematics of how this works, but conceptually it is an objective technique to assess the sensitivity to the specification of initial conditions. And so here are the response functions we chose. We looked at moisture flux convergence, horizontal kinetic energy, and the sensitivity to the initial specification, in this case of the water vapor. So this will give us an idea of, for if we do have integrated TPW, where should we put the measurements, and then and then the sensitivity to the temperature and stability, and then the wind speed, which gives us some idea of the sensitivity to the mid to upper level wind shear. So I tried to list all of the physical factors that per the influence of development of organized convection, which these all relate to. So let's, obviously for a simulation of GPS TBW, we're looking for this. So here is our forecast verification box in terms of our domain reflectivity, and then I'm almost finished. And then here is the sensitivity to the specification of initial water vapor to the moisture flux convergence in that box. And you see that it's really sensitive to the initial specification of moisture right along those mountains. And then also when we look at the sensitivity to the kinetic energy, so the wind shear, it's where the inverted trough is located. And then if you choose a different box here in the Gulf of California, not surprisingly, it's very sensitive to the representation of the moisture associated with the Gulf surge. What's nice about this is you really can determine in different geographic locations your sensitivity to the specification of the initial conditions. This gives you some insight into where to put the observations to maximize your forecast in an observational network. So some concluding thoughts is to simulate organized convection. Obviously, we need favorable thermodynamics and dynamics accurately represented in the initial and boundary conditions of a model. Then we need a convective resolving scale to explicitly represent the storm structures by means of microphysical parameterization only, and accurate specification of observed data on the mesoscale, particularly where convection initiates in the mountains and where there are dynamic features. And thankfully, per this point, we have a lot of GPS stations located in the mountains, so we're really going to be able to test this point and when we move to the next phase of Jamie's work to assimilate the GPS TBW. And that's all I'll say.
We don't have time.
No.
Okay. Next speaker is Ariano from the University of Arizona.